if we don't have enough hardware to provide, and then it will be a problem for the teaching. But fortunately, I have seen the report one. Student, I mean, also the video student can still understand the concept and can still learn the technique by using LabVIEW and MATLAB. I'm still very happy. And but into closer loop for the student early feedback survey. So I just want to do a polling to see whether is that this subject is too challenging? Should we slow down, or should we keep this pace? Or we include some maybe include some tutorial in the future time, because we are mainly teaching the two software and also the concept and the fundamental concept. We put some video and put in the website, but maybe we previous year we also have a, uh tutorial. So maybe in the future we will also provide the tutorial as well. Um, so if a student already come, most of the student come, I will start to uh, discuss, uh, give a polling to see how is the subject going. And from my understanding, like uh, if you want to totally understand the theory behind, yes, it is quite challenging. Yeah, but my suggestion is like we first use these two software. We base on the project. We learn the fundamental, not fundamental, just the technique, and then we base on the practice. We got gradually we get some intuitive understanding, and then we start to read all the books and all some videos. You can base on the video we provided. You can you can do more and to find more video and to learn more. Um, so last week we discussed because some students didn't come, but we discussed short-term free transform because last week is a student due week, student vacation week, so we cannot force you to come to the lecture, but we provide something to learn. And I also put the lecture and also the lab video I put into the canvas. You can based on that one to learn the things. So for this week, I cannot put too much time to the short-term Fourier transform because we are stage two is also due quickly. So I want to spend some time first cover all the contents. For example, today I discuss wavelet. Uh, Maybe we cannot do too detailed. For example, the wavelet contains both continuous wavelet and discrete time wavelet. There's a lot of contents. I think that's it's a very it's impossible. I cover all the details about the wavelets because this is a very complex concept. But today my plan is first I give you an intuitive explanation about continuous uh, wavelets first, and then I discuss discrete time wavelet, and then I use both maybe first MATLAB, and then I also go to Python. Actually, Python is also powerful. The reason is I found that LabVIEW, the evaluation version, don't have the wavelet inside. So I ask some of the, I mean, one of the tutor, maybe Jeff you or Carrie gave you some explanation about how to use workspace because workspace is an uh, online material. You can use workspace uh, to uh, to use live view, and in the workspace we already checked they have all the wavelet toolbox. So it's a very good toolbox. Uh, so we nearly most students come. Maybe I will make a polling later, and and then I will introduce the Wavelet. Wavelet is very important and very intuitive, very important in for recent signal processing techniques. So if you learn modern signal processing or image processing, we must learn Wavelet. So last week, I discussed short-time Fourier transform, but this short-time Fourier transform is still have some disadvantage, and also the fundamental idea is still Fourier transform. So didn't and so it's now have no fundamental change. So today, when we're talking about Wavelet, and Wavelet have lots of new idea because it is from totally new uh, idea develops the wavelet. But from a traditional point of view, I can still explain wavelet transform as Fourier transform, as a Fourier analysis. Yeah, and I will teach that very soon. So now I will share my screen. So I share my screen and we look at some. With polling. So this survey is not I mean I will not record your name and the things. You just directly answer whether this is the first because for the student early student feedback survey, one student said like this subject is challenging. So I think like maybe this is too our learning pace is too fast. Will you please do the poll to let me know what you think? That's great. So most students still think this speed is okay. So in that case, we will keep this speed. But some students also mention like maybe we need to give some tutorial. I will also uh, try to. This is not in the formal early feedback survey. It's some student told me directly. So maybe I will make some change to put some thing in the tutorial. So we learn something from tutorial. Another so I close this polling. I have another polling. So this result, most of you they agree that this is okay. Yeah, I think so in that case we keep the space, keep the base and to continue. So in the next assignment is we actually the assignment is quite similar with the first assignment. I think the main challenging is just like before we just use uh, uh, Fourier transform or FFT to do the signal analysis and the design filter. Use FIR and IR filter. The linear time invariant filter is uh, I mean relatively easy, but for the next stage is a little complex, but the overall procedure and overall requirements is the same. This time we give you a piece of non-stationary signal. Uh, have you read the signal yet? Because yeah, last week I put it, Curry put the signal. He mainly download from the FizzleNet, and he put some deliberately put some uh, stationary, non-stationary signal, so you can make analysis. And today we want to uh, just teach you how to deal with a non-stationary signal. Last week I discussed short-term Fourier transform. I remember I put some. So for short-term time Fourier transform, actually the formula is still maybe you still remember, it's just put a window. Actually, fundamentally still Fourier transform. So, but the window, if you select the good window, they also have inverse short-term Fourier transform. And I mentioned about one is also have discrete time, Fourier transform, discrete time short-term Fourier transform, and you can recover the signal as well. And also I discussed about the Heisenberg uncertainty theory principle. Actually, if you here we want to reach to the limit, we need to design the Gabor discrete representation. And at that time, we also mentioned like short-term Fourier transform uh, have some limitation. That means they are if you fix the window and then if you do the short-term Fourier transform, you can only get one either good in frequency domain or in time domain. So they need compromise. If you want to change the scale, you need to do another short time Fourier transform. That will be very time consuming. So that's the one advantage of that. Another advantage is like like the short-term Fourier transform is still from the Fourier transform. So their fundamental is still related with sine wave. Sine wave is quite smooth. It's smooth signal. Actually, you can do as many as derivative you want. They always is I mean smooth, quite smooth. And for in real situation, there's lots of signal. They're not smooth. For example, even for the step signal, they are not smooth. So in that case, if we want to represent or approximate the signal, this is not efficient. So sometimes you maybe heard about you want to compact the data, and then you transfer the data to somewhere, like YouTube, because they have a very good compact method. They are quicker. You can read the YouTube, watch YouTube very quick. But what's the technology inside, we don't know. But for the wavelet is one function is like they can for example for very uncontinuous non-continuous signal, they still can use a very sparse representation. That means use only several uh, parameter or several coefficients. They can express the signal. So today we want to discuss what's wavelet. So I put have you read my I put UTI and some video. I think what I want to do is And I put some video in the UTS online. Uh, Not UTS online, sorry, Canvas. I think I put a lot of reading material and the video. This a very important thing to understand Wavelet. So maybe we look at uh, a tutorial material. So what is Wavelet? So there's a history of wavelet. So wavelet is actually, you can see the history is developed. The earliest wavelet is 1910. So that's more than 100 years ago. They already developed, but at that time the name is not wavelet yet. Uh, but that's the first one. But in only in 1980, around 40 years ago, the wavelet concept come out. And then they develop different kinds of wavelet, um, and also they developed the multi-resolution method. We will discuss it when we discuss discrete time wavelet. We will discuss about multi-resolution. And recently, not recently, it's in 1988, they designed the compact support orthogonal wavelet. So it's Dubash. She developed these things. And finally, there is a fast wavelet transform, like a fast Fourier transform. They use a filter to implement discrete time wavelet. So this is all the mathematicians developed this kind of method, but they are very practical. So here they explain that they steal from the uh, Fourier analysis point of view to explain wavelet. So now maybe I just like I give you a brief idea why they do the Fourier transform, or why they develop wavelet transform. What's the reason? The basic idea is like, for example, in the like when you study mathematics, like you want to approximate a vector, or you want to have a good way to approximate vector. You something like this. Uh, you use a coordinate 3D coordinate, right? 3D coordinate, and then you can project the you can project the vector to all the axes, all the axes, and then when you do calculation, that will be very easy. For example, if two vector plus them together, if two vector plus them together is relatively simple. How to do that is very just like before it's a vector calculation, now change to algebra calculation. So that's a kind of approximation. Uh, so also we need to consider about the axis. So also the coordination. Actually, this coordination is good because each exercise they are orthogonal or they are perpendicular. That means they are independent. So that's a very good thing. For example, we just learned the Fourier transform, right? Fourier series. Fourier series actually is you can consider as a in the in a similar idea, but it's in the infinite dimension uh, coordination. So for the Fourier analysis, for Fourier series, what's the axis? Do you still remember? Actually, the axis is a sine cosine function and the DC component. So it's a so you project to you treat the function, a periodic function, as a vector, and then you project this vector to all the axes. So you have infinite number of axes. For example, you have DC component is one, and also you have a sinusoid. For you have a first harmonic, second harmonic, third harmonic, and then all this one is the axis, and then you just project to this axis. And it is proved that all the axis is orthogonal. And if you do some little scaling, you can also make it is a unified orthogonal. That means themselves project itself, it is one, so it is unified. So that's why you can directly calculate the Fourier series, the coefficient, just use projection, just directly project uh, the function to the to one of the axes. Actually, the projection is they called inner product. But for the function inner product, actually is like is a integration. Or it looks like a convolution or something like that. So that means convolution can implement the projection. So for the function vector. For the real vector, you know, you use a dot product. I'm not sure you still remember dot product. Dot product is a kind of inner product. It's a special inner product. So inner product is very general. Like if they satisfy several rules, and then they can call inner product. So they can very abstract. It's not necessarily an integration or dot product or things. They are very complex, very abstract, but they only need to satisfy, for example, three or four, I think it's four fundamental rules, and then you can see this is a inner product. The good thing is like this is very general. If you can find any kind of product, any kind of product to satisfy the inner product uh, rule, and then you can use all the result developed for inner product. So so that's mathematician. Mathematician always thinking about make things more general. So after they developed the Fourier transform by Fourier series, Fourier transform, Z transform, and then they think about can we find some more new uh, axis, and this axis if it's orthogonal, and then we can still use the same idea project in this kind of uh, axis, and then sum them together, and then it will be a new kind of Fourier analysis. They call the Fourier analysis in Hilbert space. So you know Hilbert space is kind of some coordinate, but they maybe have an infinite number of coordinates, so infinite dimension. But if you define the inner product and you define the projection by the inner product, and also you define the you can use the inner product to induce a distance. So actually self uh, inner product will generate distance. So the distance, if satisfy, for example, the positive needs and also the triangle requirements, that means two sides plot together will greater than any one side. So this kind of uh, rule, very abstract rule. But if you satisfy this rule, and then you can construct a Hilbert space. So in Hilbert space, you can do all the projection. And based on this idea, the actually the uh, wavelet, they produced the wavelet. So wavelet, we maybe go to a video to see the wavelet. What's the wavelet? I think this is a very good video I put here, but I read this one. I think you have read this one. We have read this one a little bit. I think the maybe see why we. So what's the wavelet? The history they developed mathematician based on this fundamental idea. They developed the wavelet. So before that's they find some. They first they need to find wavelet. The wavelet is something like sinusoid function. Actually, sinusoid function satisfy the orthogonal, also unified orthogonal property. So, but you can find some other wavelet. So the first wavelet, so another access. So the first one is called Harry families. Harry, this mathematician, he developed the first, I mean, the different wavelet. The wavelet is very simple. Actually, it's just like a, a, a rank function. And the rank function, not is rank, it's a two rank function, uh, like sinusoid, but two ranks merged together. You can search in the maybe in the website. I find the Haar wavelet. Maybe Haar. You can see what Haar wavelet looks like. Something looks like this. So this is Haar wavelet. So you can see quite simple, but this is a orthogonal wavelet, and based on the projection idea, they developed Harry developed the first wavelet approximation, and later in the 40 years ago, this mathematician developed another method, uh, find other wavelet, so they are also orthogonal. And in the future, if you find some other family, you can also use this same idea. It's just like you can see the idea is like, for example, there's a function. You think if the function can be a summation of the phi k is the axis. You have a lot of axis, the wavelet, right? They call the wavelet. Small, I mean, this you can consider as axis. This is the projection coefficient, just like as a 3D coordination. This is the projection. So if you can, uh, if this one is orthogonal, so you can see this is the orthogonal property. This talking about you find another orthogonal, this dual orthogonal. Maybe this is a little complex, but some wavelet the self is already orthogonal. But if you sometimes you cannot find orthogonal, you can find the dual orthogonal one. So this is a dual orthogonal one, and then they are uh, maybe you this is a dirt function. That means if I and j is equal and then equal to 1, if I and j is not equal, it's 0. So this is a like some like if itself is 1, that's good. That's called unified. But if different axes they are 0, that means they are perpendicular or orthogonal. So this is the idea. And then if based on this one, you can easily find projection. For example, you want to calculate AK. Rather than you project on the phi k, you project onto the dual orthogonal uh, axis, and then you do the calculation because they are orthogonal, and then they change to 1. So here become 1. So you directly get AK. So that's a good property. And then this good hint, all this kind of most of this kind of wavelet is based on this fundamental idea to develop and to calculate. So the calculation will be faster as well. So that means you can, because they put even the this is for Fourier transform. Fourier series is a special case of this kind of wavelet. So we look at this is give some example and also multi-resolution analysis. We will discuss in when we discuss discrete time wavelet transform. Uh, so this multi-resolution analysis. Um, the mathematics behind maybe is too complex for you. I just want to give you some cool picture, and then we go to the application point of view. But the application, if you want to, you use the tools, you get the result. You still need to explain the result. So that's why I give you some fundamental uh, concept. So this called fast. This is the fast wavelet. They use a filter to implement I will discuss later. It's very innovative to implement wavelet convolution. And you can see the I think the also 2D wavelet we also will introduce later because currently we are the 1D wavelet. 1D wavelet is the signal we are currently deal with. It's all like EN, DE, EG. They are 1D. What that means, they only have time as a as a input and uh, only have one dimension in the time. So, but some you have two dimensions. X, Y is an image. So image processing can use can use wavelet very well. Although recently we use deep learning or something or artificial intelligence can do the image processing, but wavelet is very is still very useful because they can use wavelet to help you to find the features for the classification. In the stage 3, some of the projects may be related with the image processing or with signal processing. For example, you can use wavelet to transfer a ECG signal to a 2D signal, and then you can use even uh, deep learning tool, or you use some image processing to deal with. But so 2D wavelet is very good in the one thing is like he can compact a figure a picture with use small memory and easy to distribute in the website in the internet. So this is discuss about see here is the example. So because you have a X and Y, right? You can do the you know, like after digital, I will introduce the digital wavelet. Digital wavelet they use low pass and high pass to filter the signal. And for this image also you can do in the X direction do low pass, high pass, and Y direction do low pass, high pass. Normally after low pass they call the approximation of the signal. So if you pass two low pass, actually it's approximation. So you can see this figure and this figure quite similar, but this is approximated. So they neglect all the detail, lots of detail. So here is in the horizontal part is analog, is approximation, and then this is the in the downside is like is low pass, so it's approximation. So here this one is all detail. It's not no matter in X direction and Y direction, all detail. So you look at these things, maybe you only can get some edge of the figure. You cannot see the whole picture. So normally for the you will see for the 1D signal is similar. You maybe approximation is more important. But I will discuss this maybe in later future. Uh, so you can see the image looks not very different, but they use very less memory to store these things. So they discuss both continuous wavelet. So the continuous wavelet is something like this. I will discuss this very important concept for the wavelet here. You can see for the after I go to the application point of view, so they introduce so many uh, they even introduced a short-term Fourier transform last time, and then here is why it's better. Like I discussed last week, is like for the Fourier analysis, Fourier transform, they always like in the you can they assume the time is all the in the time the signal doesn't change, so they only have a frequency information. But for the short-term Fourier transform, you can have different time information, but you cannot change the scale. But for the wavelet, you can both change the time. You can have a time uh, indication, and also you have they call this is not frequency, but they call scale. Scale is opposite with frequency. I will introduce later because scale, I will do some pooling uh, questions by some example, because this if you want to totally understand the scaling, we need to do some exercise. And actually, scaling is related with the frequency. And so they're talking about some common used Kalman filter. I mean the wavelets, and I just want to see the where's the application, right? So application, why we learn Wavelet. So Wavelet is this application. One is like image compression. So I already explained like you can use small storage uh, memory to store the large lots of image. So you can see this is the original one, but you can use uh, uh, you can see they use two different called one DCT based and this is Wavelet based. Wavelet based you can see still very clear, close to the original one. So that's some also you can use for each and corner detection. You already see like for the detail is you actually emphasize the high frequency component and then you can detect the edge. So that's for and the corner they can detect. So it's good and also pattern recognition. I mentioned about you can use this one to get the features of some signals and then do the classification and also can filtering. I will maybe use an example like MATLAB can use discrete time wavelet to do denoise, can get rid of because that's powerful than the FIR and the AIR, much powerful. They have a they can use different level of denoising and also can use, for example, analyze the ECG. Of course, other signal can also do the analysis. So it's a powerful tool. So before we go to continuous wavelet, maybe I think the best way first we look at what's continuous wavelet looks like. This continuous wavelet. So just the idea, if you find the phi is a like you can treat this one as a sinusoid. Uh, it's a generation of sinusoid. Is the one is orthogonal each other, and then you do the just do the convolution, or you do the projection, or use inner product, and then because this one is first they are unified, right? The unit is one, and also this one is if it's uh, orthogonal, that's good. If not orthogonal, you can find a dual orthogonal function. And but you can see the function looks like this. You can see you have s, you have u. This function, if the original one is phi t, can you imagine what's phi t minus u over s? So the s actually is give you a dilation or the give you the scale, like something you can uh, push, I mean compact the signal, or you can dilation the signal. So make this called scaling factor. And also you have a transportation vector, this u. You can move the signal to move the function to a particular location. So you know like for sinusoid, like you because you don't have time, you cannot have option of time. You only have option of frequency. So for the Fourier transformation, you have f is a frequency. Actually, it's corresponding to the s, right? But they are opposite. That means the big F is corresponding small s. The small s is corresponding to big F, or the big S is corresponding small f. We will look at they call the scalegram. Scalegram is similar as spectrogram, but they are mainly for wavelet analysis. And then you can calculate the coefficients by using this called inner product. Is actually is a convolution. This not is a integration. Here is the ft is the function you want to do the CWT, continuous wavelet transform, and then you do the integration, just like to project to this axis. This is the wavelet. So in that case, you can calculate all the coefficients. Uh, uh, that's the continuous wavelet. So this is one example of the continuous wavelet. It's a 5T like this, and other things. So this called the Mexican height, Mexican height. So you can see their average is actually should be 0. So for the wavelet, and also wavelet itself is also related with frequency, but they are not equivalent. Why? Because sinusoid, their frequency is only one for one particular sinusoid. The frequency is one. It's a particular one point. It's for example, its frequency is 1 hertz. So in that case, the sinusoid is 1 hertz. But for wavelet, actually they have several. They have called they have a band pass. Uh, looks like a band. So in they have center frequency. That if there's a band, you have a center. So we are more interested with the center frequency. We will discuss when you use a wavelet, you need to know what's the uh, center frequency. So for example, this one is not only one frequency, it's a some frequency band, but they have a center, it's in the middle. It's called the center frequency. We're interested with the center frequency. We will use example to explain later. But before we go ahead, I still want to use this time to learn something fundamental, like how to analyze, how to understand the scale, and also how to understand the transportation. Now let's look at the video first. I think there's a very good video. I suggest you to watch because we don't have time in the class, but we have a time when you go home. You just watch video, maybe more clear than my explanation here. Is here. So this is a very this several very good material. I didn't go through here. Uh, here the is a slides, wavelet slides. We talk about the fundamental. So this is similar with the one is scaling and the translation. So this is a two factor. Tau is translation, S is scaling, and also they talking about CHT, continuous wavelet transform, and they discuss lots of things. You can have a look. So this is because the time is too short, we cannot go here, and but we can go. So this some other reading material. So for this one, you should read this one. So this talking about this one talking about the short-term Fourier analysis and wavelet. So how they jump from short-term Fourier transform to wavelet. So this one is also introduce why wavelet is good. So if you are small, very discontinuity, then high frequency component, you can see wavelet can exactly catch this one. So and those, what is wavelet analysis? They explained quite well. So this part you should read, and also they introduce what's the scaling. So here scaling. Here the scaling is not 2, it's 1/2. So it's in the denominator side. So this is a you can see this opposite with the frequency. So this frequency, what's the frequency of this one? Uh, the 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 frequency. So increase when the frequency increase, actual scale drop. It's the opposite. So we need to be careful. I will use I mean to put some more explanation, and then we continue. So I think this is one good reading material. Another reading material, I think I put lots of reading material as well. I don't want to go to all of them. For this one, because this is very long, this is actually it's Wavelet toolbox of MATLAB. They have like dictionary. You can find anything you want. So many things. Actually, maybe you can based on this one find something. Even in the website, they have a YouTube. You can find some YouTube to directly explain, maybe quicker. Uh, I give you some reading guide. It's like you just read page 3 to 15 because in the MATLAB they have a like an app. You can use that one to do the wavelet analysis. Uh, Read this part, and also we have a tutorial. I already introduced this tutorial, and another tutorial is also useful. And also there's a research paper. This is very complex research paper. They use a filter bank to implement the DWT. This video is a very good video, and this tool to know the basic of wavelet. So I will quickly run this one together, and I will show you which part is more important.
Hello everyone. In this introductory session, I will cover some basic wavelet concepts. I will be primarily using a 1D example, but the same concepts can be applied to images as well. First, let us review what a wavelet is. Real-world data or signals frequently exhibit slowly changing trends or oscillations punctuated with transients. On the other hand, images have smooth regions interrupted by edges or abrupt changes in contrast. These abrupt changes are often the most interesting parts of the data, both perceptually and in terms of the information they provide. The Fourier transform is a powerful tool for data analysis. However, it does not represent abrupt changes efficiently.
So this one taught you like why we think about wavelet. Wavelet can do very uh, discontinuous or very high frequency signal, very efficient. And
The reason for that is that the Fourier transform represents data as a sum of sine waves, which are not localized in time or space. These sine waves oscillate forever. Therefore, to accurately analyze signals and images that have abrupt changes, we need to use a new class of functions that are well localized in time and frequency. This brings us to the topic of wavelets. A wavelet is a rapidly decaying wave-like oscillation that has zero mean. Unlike sinusoids, which extend to infinity, a wavelet exists for a finite duration. Wavelets come in different sizes and shapes. Here are some of the well-known ones. The availability of a wide range of wavelets is a key strength of wavelet analysis. To choose the right wavelet, you will need to consider the application you will use it for. We will discuss this in more detail in a subsequent session. For now, let us focus on two important wavelet transform concepts: scaling
yeah, this is one important one. It's called scaling. And then it's transportation,
and shifting.
or called
Let us
shifting.
start with scaling. Say you have a signal psi of t. Scaling refers to the process of stretching or shrinking the signal in time, which can be expressed using this equation. S is the scaling factor, which is a positive value and corresponds to how much a signal is scaled in time. The scale factor is inversely proportional to frequency. For example, scaling a sine wave by 2 results in reducing its original frequency by half or by an octave. For a wavelet, there is a reciprocal relationship between the scale and the frequency with a constant of proportionality. This constant of proportionality is called the center frequency of the wavelet.
So the center frequency I just discussed is very important. You can see how to calculate the center frequency. For example, in your report, if I ask you what wavelet you use, what's the center frequency, you maybe can use.
This is because, unlike the sine wave, the wavelet has a band pass characteristic in the frequency domain. Mathematically, the equivalent frequency is defined using this equation, where Cf is the center frequency of the wavelet, S is the wavelet scale, and delta t is the sampling interval. Therefore,
So the frequency is related. One is center frequency, and also related with your scale, and also related with your sampling frequency. The sampling frequency, of course, the faster, and then the frequency is higher.
when you scale a wavelet by a factor of 2, it results in reducing the equivalent frequency by an octave. Here is how a SIM4 wavelet with center frequency of 0.07 Hz corresponds to a sine wave of the same frequency. A larger scale factor results in a stretched wavelet, which corresponds to a lower frequency.
So this video is quite useful to understand the scale and the shifting, and also the fundamentals of wavelet. And the next one we'll discuss about a very important concept is discrete time wavelet. And yeah, we go to the next one. So this one is also good. This is also good to introduce introduce and then this one is called continuous wavelet and discrete time wavelet. Discrete time wavelet is very useful, can do the fast wavelet transform, and the concept is use a filter bank to implement. So they use several, for example, four filter to implement one times of one level of DWT. So here is give you an example.
In the previous session, we discussed wavelet concepts like scaling and shifting. We will now look at two types of wavelet transforms, the continuous wavelet transform and the discrete wavelet transform. Key applications of continuous wavelet analysis are time frequency analysis and filtering of time localized frequency components. The key applications for discrete wavelet analysis are denoising and compression of signals and images. As I mentioned in the previous session, these two transforms differ based on how they discretize the scale and the translation parameters. We will discuss these techniques as they apply in the 1D scenario. Let us take a closer look at the continuous wavelet transform, or CWT. You can use this transform to obtain a simultaneous time frequency analysis of a signal. Analytic wavelets are best suited for time frequency analysis as these wavelets do not have negative frequency component. This list includes some of the analytic wavelets that are suitable for continuous wavelet analysis. The output of CWT are coefficients which are a function of scale or frequency and time. Let us now discuss the process of constructing different wavelet scales. Recall from our previous video the signal and compared with the original signal. You can repeat this process for all the scales, resulting in coefficients that are a function of wavelet scale and shift parameter.
So in that case, this idea is quite intuitive. You just like use different scale and then compare with the original signal. Actually, it's convolute with the original signal, and you can calculate for one scale. You can calculate a number of uh, a number of the coefficients, and then you change a different scale. You have a different one. Actually, in that case, you get before it's a signal, and now you have a image, something like.
To put it in perspective, a signal with 1000 samples analyzed with 20 scales results in 20,000 coefficients. In this,
So in that case, the data become bigger.
you can better characterize oscillatory behavior in signals with the continuous wavelet transform. The discrete wavelet transform, or DWT.
Now, discrete time wavelet transform. This is also called the multi-resolution analysis. So this one is very useful. Can implement in real time by using filter bank.
Is ideal for denoising and compressing signals and images, as it helps represent many naturally occurring signals and images with fewer coefficients. This enables a sparser representation. The base scale in DWT is set to 2. You can obtain different scales by raising this base.
So this is scaling, but We also
scale
link up.
to integer values represented in this way. The translation occurs at integer multiples represented in this equation. This process is often referred to as
So,
given a signal
so
S.
most important is so most important is here they use multiple I mean this filter bank to implement the DWT. So you have see have one signal in, they can use low pass and high pass, and then they get positive I mean get the approximation and the detail or called noise. Detail is something related with noise, but the approximation is like single. And then you can do an after the down sample, you do another time because the down sample is keep the signal length is the same as before. So they do after filtering the down sample as well.
First filtered with special low pass and high pass filters to yield low pass and high pass subbands. We can refer to these as A1 and D1.
So this A1 is the approximation because this pass low pass, here is high pass. This detail, the D1 is the first level, and then they do the you can see they do the down sample, and then do another.
Half of the samples are discarded after filtering as per the Nyquist criterion. The filters typically have a small number of coefficients
This high
that
pass,
result in
low
good
pass.
computational performance. These filters also have the ability to reconstruct the subbands while cancelling any.
And the good thing is like the you can see they also called low pass, but for different wavelets, the low pass coefficient is different. All the high pass, they are all called high pass, but the coefficient is depends on the what wavelet you use. So that means the coefficients of the filter is can determine what wavelet you use. So it's amazing. Like so that's my mean you can implement the DWT just use filtering.
Any aliasing that occurs due to downsampling. For the next level of decomposition, the low pass subband A1 is iteratively filtered.
So they redo this again, exactly repeat previous stage, but now they use A1 as the input.
By the same technique to yield narrower subbands A2 and D2 and so on. The length of the coefficients in each subband is half of the number of coefficients in the preceding stage. With this,
So this the DWT have different level, and then when you, for example, classification, you have different level of D component, for example, D3 or A3 or something to pick up the feature. So and also you can do denoise. For example, you denoise D3 coefficients, make it 0, or use some technique. They call the threshold technique. Actually, in the MATLAB, they all have. Now we go to, I mean, I show you MATLAB to implement how difficult or how easy to implement, for example, CWT. So CWT, this is a you use a continuous wavelet. So you can see the speed is still very quick. So this is the original signal. This is the original signal. This is for different stage of the noise. So this is a approximation in the DWT. So this one, this is a CWT. You can see in the CWT you have a time. Time you use the parameter B. So S is shifting. So you can give you a time change. Because my input is sinusoid, so looks no spark. But here I have a scale as well, scale A. This is opposite with the frequency. For example, 26. Actually, the frequency here is higher. It's lower than 21. So 21 corresponding higher frequency. So this scale. This called scalegram. So opposite with spectrogram. Spectrogram last week we discussed use MATLAB. You can also join. For this one, it's very easy. You just one command, you can implement CWT. So you can see here I use CWT, and then this is the input signal, and I use uh, Dobash 4 wavelet. You can use Dobash 1, any wavelet you can select, and this is the DWT. You can see you only use DWT, and then this is the level 1, the first level, and you can pull out the first level, and you can also have a different level. You can continue. You also have I think we have a for discontinuous signal. This is CWT. Still remember? You remember last week I discussed. I used short-term Fourier transform. I use also similar signal, this sinusoid with changing frequency. So you can see the wavelet can clearly identify two very clear change. So we also have some denoise one, I think DW test. This is a DWT2 DWT1. You can use DWT implement CWT as well. So this is an example to analyze signal. So because time is not very, I mean, we still need to be quickly to read. But to be honest, it's very straightforward. You just this is use a denoise. You can see this is a original signal, noise signal. After denoise, you can see very clean and not damage the information real signal. I mean the signal only get rid of noise, but the signal is totally uh, preserved. So in that case, but for the normal DWT and the CW, sorry, for the DIR and the IR, FIR, you cannot do as good as this. So they have a, you can see they have different approximation. So this one is have original signal level 1 detail, level 2 detail. They all give you all the details signal. So you can get rid of some noise, which level you want. So it's quite convenient. So in the lab time, uh, Carrie and Jeff, you will help you to design this kind of wavelet as well. I'm not sure in the short-term Fourier transform last week, do you start to play around with the signal? Today we will mainly consider the DWT and CWT. And one thing is I find this very disappointed because I find like most live view license they are not provide wavelet function. But I discussed with Jeffy. Jeffy said like in our workspace, actually in the live view they have the wavelet function, so you can directly call that. So in that case, you have two options. You can either find the full version live view with the wavelet toolbox. Another is you use workspace. Jeff, you said it's not that slow, still okay. Just log in is hard, but if you use it, it is still okay. So my suggestion is let you follow Jeff to see how to use workspace to do the level analysis. Another option is use Python because recently I learned Python and then I found that Python the signal processing toolbox is quite powerful. Uh, this is a short-time Fourier transform. Last time I show you already. They also have a wavelet. So this is a wavelet transform for image processing. So this is this is an original picture. Sorry, this is approximation. Original didn't draw. This is a approximation one, which use very less memory. and then this horizontal detail, and this vertical detail. That means the low pass in the horizontal, and this is low pass with the vertical, and then this diagonal means all use uh, high pass in the X and Y. So this is you can see that it's very short as well. So you can use you also can use Python. So they have also CWT. You use Python also, they can do CWT and match with a different frequency scale, and so they can also CWT as well. So before I finish the lecture, I want to do some little pooling question to just want to emphasize the scaling and the shifting, the two very important concept. And I will see like because I remember in the first lecture there's one particular question, quiz question, with related with these two factors. Today I also discuss with this quiz question. This quiz question is very relevant with Wavelet transform, the concept. They use scaling and shifting parameters. So we look at maybe we go. So I give you so many questions. Maybe we one by one. So first one. So for this one, which is dilation parameters for this one? Which is the dilation parameter? So the first question. This is relatively simple. So the first one. So can you do that? Hi, Jeffy, Curry.
Yes, I'm here. Yep, you're here.
Can you hear that?
Yeah. Yes.
Yep.
Yeah. Can you do try to do the first one?
Yeah.
So I mean I cannot see anyone to do the
Yeah.
cannot do it. Probably is the issue is I use only if you cannot do it, maybe I cancel this one, cancel this pulling. I think maybe I not make it working. Oh, so you can do it. How about student? Can you try this four question? So this one I cannot see your name, so you just do it. Don't worry. No one can see the who select what question, so don't worry. Just like do your best. Okay, so for the first question, which one is a dilation parameter? Dilation actually is a scaling parameter. Actually, scaling parameter. So in that case, which one is correct? If scaling parameter. Sorry, I should use scaling parameter for the first one. So it's A. So A is scaling parameter. So a B is a shifting parameter. So this is a standard format. T minus B divided by A. You need to have bracket. So this is standard format. So the A means the dilation or means the scale. You push, you stretch, or you push, and the B is the shift. Where you shift the signal. So this is a fundamental description of both dilation and shifting. So this you need to remember this the format. So in that case, you can base on this one to do all the other questions. So the first one, ft is a periodic function, and its period is 1, and then the period of this one, so you can see the scale is 2, right? So that scale is 2, and the shifting is 3, is a minus 3. So it's 3. It's actually is a shift to the to the right hand side for 3 units, but its dilation is make it more compact. It's more increase the period. So in that case, the second answer, so increase 2 times. So the question 2, the second answer is correct. So question 1, the first answer is correct. So it's good. So we got a good result. So for the ft is if it's sine t, so we still if we use this format, so this one should change. So it's a 2t. It's a t minus 3 divided by 2, and then the in the denominator half, because it's half, right? So in that case, the scale is half. In that case, your previously sine t was the period. So period is 2 pi, right? Sine t, the period is 2 pi, and then if it's half of 2 pi, in that case it should be 1 pi, right? So in that case, the period is pi or 4 pi. 2 pi is not right? Because sine t is 2 pi. If sine 2t minus 3, then this one have a high frequency, right? So in that case, this one should be pi. So this is pi. So in the question 4, so the rec function, this rec function, if ft is rec t, the center for ft times t minus pi is at. So you still need to write in the standard format here. So in the standard format, what's the a and what's the b? So the a is half. A is half, right? A is half. So how about b? B is half pi, right? Is half pi. In that case, they move to minus half pi or move to positive half pi. The center of this one, I think it should be the move to the positive half pi, right? Right, move to right hand side, right? In that case, the question, the selection 0 point pi, the third one is correct answer. So this is a very good exercise, because if this is a wavelet function, you need to find the A and the B. One is scale, one is shifting uh, parameters. So in that case, if you look at one, for example, continuous wavelet, here is continuous wavelet, for example. Here, this one is maybe I read, I mean, use MATLAB. One is go the continuous wavelet. So this is continuous wavelet. You can see here is a B, is a shift, is a time shift, and then this is a scale. So you need to understand the scale, what that means. So the scale, the bigger, actually the frequency is lower. Now we look at the quiz question. Last time I did a quiz question for this one. Do you still remember this question? Actually, I remember I did it in the class, but I didn't give the right answer. I didn't finish that. But this is now is a very good time. We think about this question again. Um, Actually, you first need to draw the figure of this one. This one you have two methods to calculate, because later we will have some tutorial session to just discuss about some questions. But this one I just use maybe 10 minutes to quickly explain how to find the right answer for this one, because this is related with Fourier series. So in that case, this one is this function a periodic function, right? So periodic function. The period, actually the period is 4, right? The period is 4. And if you want to find the Fourier series coefficients, or you want to find third harmonic components, actually you have two ways. One is you use the formula. You have a Fourier series formula. Actually, in your first assignment, you have the formula in the lab. Assignment 1, you have two exercise. The one exercise is calculate mean to do the Fourier series. You need to calculate the coefficient, and that one you can have formula you can directly calculate. That's one method. Another method is you use the relationship between Fourier transform and the Fourier series. So there's formula. So in that case, you don't worry about you first treat it as a non-periodic signal. You just pick one wave, and then you do the Fourier transform. And then you, based on the Fourier transform and the Fourier series coefficient relationship, you can calculate the G3, actually the third harmonic coefficient. If the coefficient is a complex number, and then you can calculate the magnitude and the angle. And the angle, you can see whether it's a 90 degree or minus 90 degree or 0 degree. So you have this choice. Now because I don't have the breadboard, I write in the paper. Maybe we can share this result. Sorry, I cannot put. So for this one, the first solution is just you directly use Fourier series formula. So this is Fourier series formula for G3. So this is 1 over T0, and the integration from minus half T0 to positive half T0, and because the signal is A times rect T plus 1 minus 4n divided by 0.2. So you can directly use the formula to calculate. But the difficulty for this one is you need to use the one we just discussed, the standard form. We find the scaling and we find the shifting. So here we find the first wave. Actually, the wave should look periodic. Like this is rect function. Rect function is from minus half
change it to 1, and the positive half get to 0. So this is a first reg. This is a standard reg function. But when you change scale, this scale means that you change it to 0.2, and then the scale change before is 1, right? It's 1 scale. The the width is 1, but now the width change to 0.2, and also this periodic function. So you can have different n. For example, if n equals 0, you get this one. So this one n equals 0, you can t plus 1. So the shift is a shift to the left hand side 1. So you put a minus 1 here, and this is the width of the reg function. So it's a 0.2. So you have a minus 1.1 and to positive to the minus 0.9. So this is a one period. You also have other period. I didn't write all of them because I use only one. I can calculate the coefficients. So this one is for n equals to 1. If n equals to 1, this one is t plus 1 minus 4. N equals 1 is minus 4. That means equals t minus 3. Minus 3 in the shift parameter is 3. So in that case, you need to move from here to right hand side to 3 up to here. So but the width is still 0.2. So you start from 2.9 to 3.1. So this is the figure, and then you can just use the formula. This will be easier because you know this is the first is 1 over period. So period is 4, right? So in that case 1 over 4, and then your integration, because other part is become 0, right? Other part, in that case, you are from infinity to from minus half t to positive half t. Actually, it's only from minus 1.1 to minus 0.9. You have value. So this value is a. So a times the, like for Fourier series is e minus j 2 pi f. Here is a 2 pi f, but nf. So f here, f0 is a 1 over sampling rate. So the frequency is 1 over 4. So that's the frequency. But you want to calculate the third harmonic. So you times 3 and then t. So this is the formula here. I just, based on this formula, I put the value and get the integration. So you need to do the integration. So this integration is something looks like this. And you continue to calculate, and you get is a minus j times 0. Sorry, here is wrong. Here is correct. So this should 1 divided by 4. Here. So this one is wrong, but here is correct. Final is minus j 0.0482 times a. So this is a real number, right? So we actually, if you calculate wrong, doesn't influence your selection. So this basically is minus j. So minus j, what's the angle? Actually, it's minus 90. So that's why the answer should be minus 80. So the second one is correct. But you can see, if you want to get the right answer, the most important thing is here. So you need to draw the figure things, and that's why if you want to totally understand Wavelet, you can do some more exercise for the changing of. There's a same function, but if you change the scale, shifting to the different area, different position, and then you can get different things. And so that's this question. I want to use this question to give you some motivation to learn the wavelet as well, and also have another method. This method is quite simple, quite straightforward. You just use this relationship between, this is a Fourier transform. Fourier transform. If this n f0 is a sampling rate, is 1 over 4 in this problem, and this is the sampling rate as well. So this Gn is a Fourier series coefficient. This is G F is Fourier transform. This GF is Fourier transform. So in that case, we first need to calculate the GF, the Fourier transform. So here is the original function, right? I only pick one rec function, and then I can do the Fourier transform. Fourier transform is very straightforward. They have a property, and then you can directly write the Fourier transform like this, because first a scalar. If you scale, you need times here 0.2, and sin sinc, because the rec function, the Fourier transform is sinc, and then you 0.2 put here, because here have a time shift, right? You time shift. So here you also need to write in the exactly this form. You cannot put separate as 1 and the t. So you need to write exactly this form. So why this form is so important? So this scale, this shift, and then the shift, because it's positive 1, shift is positive 1. So you need ej2 pi f times 1, and then this is a Fourier transform of a rec function, and then you use the formula G3, and you put n3 as well, and then you just put f as n as 3 times fs. This is a frequency, and then you sync, and then you do this one is f is also 3 times the fs, right? So in that case, it's just put g and f0, and then you can get this one. You can easily get is a minus j 0.0482 times a. So it's same as the previous result, but this is a little simple. No need to do integration. You can directly based on the property of Fourier transform, you can get this result. So the fundamental thing I still want to emphasize is this format. So you still remember the pooling function. I will do the repooling again to see whether you can get the right result, and then we go to the lab. So will you please quickly finish this one, and then we finish today's lecture. No one want to do the voting, right? In that case, we stop. We stop. Okay, Jeffy. Hello.
Yeah, I'm here.
Yeah, maybe Jeffy, you start to introduce the live view first,
Yeah,
and
yeah.
especially how to use how to use the